This is the Chem 1 lecture over molar mass and mole calculations. So we left off talking about how a mole of anything contains 6.02 times 10 to the 23rd of them. So if we had a whole mole of aluminum, it would contain 6.02 times 10 to the 23rd atoms. But how on earth can we count something we can't see? Just like if we had a big bag of BBs, these little metal balls here, how on earth can we know how many are in there? Well, if we knew how much a dozen weighed, then we could then weigh this whole bag and find out how many dozens are in there, and then maybe doing some dimensional analysis actually find out. So it's counting by mass. Basically, it's a way to create a connection between particles and mass. So in order to determine how many BBs were in that bag, we would need to know the mass of a dozen of them. Then we could calculate it. So we need to know the mass per mole of things. Well, that is called molar mass. That's how many grams there are of something for if you had a mole of them. Now, molar mass has a lot of different names. Including formula mass, formula weight. Those tend to be for your ionic things. Let's see, you've got molecular mass, molecular weight. Those tend to be for covalent things. So there's a lot of different names, but the big thing is that they're all how many grams one mole of something weighs. Now, molar masses can be reported to any number of sig figs. To keep things simple in this class, we're going to report them to 2 decimal places just because that's how they're reported on our periodic tables. That way we all match. So if you're using an outsized source, be sure you report your answer to 2 decimal places. So molar mass of elements, what you do is you just check out the average atomic mass on your periodic tables, and that would be your mass. So if you looked up helium on your periodic tables, and you look for the average atomic mass, which would be the decimal number underneath the element, it would read 4.00 grams. So that means if you have 1 mole of it, it would weigh 4 grams. Or you could say that it's 4.00 grams per mole. You want to take those 2 units together. So look up calcium, and you would read that it's 40.08 grams or 40.08 grams per mole. Last, oxygen. Heads up, oxygen is a diatomic, so it exists as O2, so there's 2 oxygens on there, so which means even though the periodic table says 16.00 grams, we have to multiply it by 2 to get our 32 grams to 2 decimals, or 32.00 grams per mole. Now, that's different when you're dealing with compounds because we have multiple atoms in there. We have to add up all the masses of all the atoms in the compound. So if we're dealing with boron trioxide first, we're going to need to know the formula for that. So diboron trioxide. We're going to add it up. So I've got a boron. Let's see, I've got 2 of them. Then I've got to look up the average atomic mass of boron. We would get it to be 10.81. Double that, we're going to get 21.62. Oxygen, there's 3 of them. We don't have to worry about the diatomic thing since it's part of a compound. It's going to follow the rules for the compound. So just 16, we're going to get 48. Add them together, and we're going to get 69.62, and the units, grams per mole. Now, the next one is ammonium sulfite. So now this one is ionic. So we're going to need to take a second and think about this formula here. I've got ammonium, NH4 plus 1, and I've got sulfite, SO3 negative 2. So my formula is going to become NH4 in parentheses 2 SO3. It's going to take 2 ammoniums to cancel out with 1 sulfite. So this compound has 4 atoms in it. We've got N, we've got H, we've got S, and we've got O. So we've got a parenthesis in here, so we need to be sure that we distribute. So we've got 2 N's, right, since there's a 2 outside the parenthesis, and there's going to be 8 hydrogens, and then the S and the O aren't in parentheses, so we don't need to worry about distributing by how many. Then I'm going to look them each up on the periodic table and find their masses. Nitrogen's 14.01, hydrogen is 1.01, sulfur is 32.06, and last, oxygen, again, don't have to worry about it being a diatomic since it's part of a compound. It's going to be 16. So then double nitrogen, we're going to get 28.02. 8 times hydrogen, we're going to get 8.08. well, 1 times 32.06, that's easy. And last, 3 times 16 is going to be 48. Add all these guys together, we're going to get 116.16 grams per mole. Notice my answer is going to 2 decimal places, and my units are grams per mole. So now we're talking about actually doing some calculations involving mass. So in the same way we use dimensional analysis to convert between moles and particles using Avogadro's number, now we're going to use dimensional analysis to convert between moles and grams using our molar mass, right? That's going to be our grams per mole. That's going to be a way to convert from grams to moles or vice versa. So our first example, what is the mass in grams of 2.55 moles of iron? So we're given 2.55 moles and we're asked to find grams. So we're going to start with our given, 2.55 moles of iron. Dimensional analysis, I know I need to cancel out the moles. And we need to convert it to grams of iron. Well, 1 mole is going to equal the molar mass. So the molar mass of iron, since iron is just an atom, just check it out on the periodic table, you're going to get that mass to be 55.85 grams. So now we can do the math here. You're going to multiply across the top and divide by 1, and you're going to get, let's see, rounded to least number of sig figs in the problem. So our least number of sig figs here is 3. So we need to round our final answer to 3 sig figs. So you're going to get 142 grams of iron. Next, let's see, the next problem, we're trying to find moles and we're given grams of nitrogen. So this one's actually going to be going the opposite direction. So here we're going to start with our given of 56.20 grams of nitrogen, heads up, diatomic. Cancel out my grams, and we need to get it to moles. So heads up, the molar mass of nitrogen is not just going to be straight up what you see on the periodic table. Since for every 1 particle of nitrogen that contains 2 nitrogen atoms, we have to double it. So your periodic table says 14.01, so it's going to end up being 28.02 grams. So diatomic. So you're going to multiply 56.2 times 1 divided by 28.02, and you're going to get about 2. Now let's go back and double check our sig figs. The least number of sig figs in the problem is 4. So rounding this guy to 4 sig figs, we're going to get 2.006 moles of N2. So now that we can convert between moles and grams, and we can convert between moles and particles, that means we can actually convert between grams and particles. So if you want to think about your mole map, previously you learned about how 1 mole of anything was 6.02 times 10 to the 23rd particles. Remember, that could be atoms or molecules. Now on the other side, we now know that 1 mole is going to equal the molar mass. Right? So now we can convert between these two things. Now, if you notice, no matter what we do, the first thing we're going to have to do is take it to grams. So if we're starting with mass and we wanted to get to particles, the only way to do that is to go through moles back down to particles, or vice versa. If we're going to start maybe down there with ions, well, first we're going to convert it to our molecules, then to moles, and then to grams. So really, no matter what you need to do, the first step you need to do is to get it to moles. So let's check out our first example. We want to find grams, and let's see, we're given 6.51 times 10 to the 24th molecules. So we're going to start with our given here. 6.51 times 10 to the 24th molecules, there's no real good abbreviation there, of nitrogen dioxide gas, so NO2. Okay, well, the first thing we're going to want to do is cancel out our molecules. And now let's think about a conversion factor. The only thing we can do is convert it to moles. So we're going to put it up top, and it's going to be Avogadro's number. 6.02 times 10 to the 23rd molecules for every 1 mole. So now we have moles. If you're looking at your mole map, we can actually go any direction. Since we need to get to grams, we know we're going to need to use our molar mass. So I chose to put moles on the bottom to cancel it out. And we need to go to grams of NO2. So which means we do need the molar mass of NO2. So which means you're going to need to grab your periodic table. So the molar mass of NO2, I'm just going to do it all the way across this time. It's going to be 1 times nitrogen, 14.01, plus 2 times oxygen, which is 16. So if you add those together, you're going to get 46.01 grams per mole. So once we have that, that's going to go in as our molar mass down in our dimensional analysis. Now that we've done that, let's see. The molecules are going to cancel out. The moles cancel out. We're left with grams. So we know we've set everything up correctly. Now all we have to do is the calculation piece. Multiply across the top and the bottom and divide. And let's see, we're going to want to round our answer to 3 sig figs since that's the least number in the given problem. You're going to get 498 grams of NO2. Okay, next one. Now we're trying to find carbonate ions given 154 grams of aluminum carbonate. So this time around, we're going to start off with 154 grams of aluminum carbonate. So now let's think about that formula. Aluminum's plus 3, carbonate's negative 2. So it's going to take 2 aluminums for every 3 carbonates. And I know I need to cancel out my grams. Get it to moles, right? The first thing we got to do is whatever we're given, get it to moles. So that means we're going to have to add up the molar mass of Al2CO3 3. So if you're going to write it out, I would do, let's see, aluminum's first, 2 times aluminum's, which is 26.98. Plus, let's see, that's 3 carbons times 12.01, plus heads up, that's 9 oxygens, 9 times 16. If you add those all together, you're going to get 233.99 grams per mole. So that's going to go way up here. 233.99. There's our molar mass. Goes right there. So now that we have moles, now we can take a step and think about where we need to go. So we need to define ions. So we're going to have to go through particles. So then you need to think about what would be the appropriate particle to use for aluminum carbonate. Well, this contains bonds, so the appropriate unit to use would be molecules. So we're going to use 6.02 times 10 to the 23rd molecules of aluminum carbonate. Now we're to molecules. Now we just need to get to carbonate ions. So now it's a ratio. For every 1 molecule of Al2CO3 3, how many ions of carbonate are there? Well, that's just a matter of looking at our formula here. How many carbonates are in this formula? Well, there's 3. So for every 1 molecule, I'm going to have 3 ions of carbonate. So I know that last step can be a little weird, that counting aspect of it. So you multiply across the top and the bottom. There we go. To get our answer. And we're going to run around this answer to 3 sig figs, since that's the least number in the given problem. You're going to get 1.19 times 10 to the 24th ions of carbonate. Should go right there.